Here you see some of the PhD students that have been involved in the work. The studies that I will talk to you about are based on material science. And material science comprises both physics and chemistry, and also some molecular biology. But in my case, it's important that you can make the materials, and making materials means the synthetic part. That is the chemist in myself. But also that you understand the properties, that you measure properties, and that you can see what you can do with these kinds of materials. Today I will talk about a very specific type of materials involving spin. You will know spin from magnetism. Many materials are magnetic, and magnetism is a very old property related to materials. But I will talk to you also not only about spin, but also about structure, because my love for materials is based on the symmetry of these materials, and I will show you new symmetries in materials, also new topologies in materials that give rise to new properties that we need for our society. So, I hope this explains my affiliation. So, I must say that the University of Groningen has an enormously powerful material science department or material science institute. One of our members got announced last month that he won the Nobel Prize, namely Ben Veringer on molecular models, also related to the materials science program. But let me talk to you about materials in more general sense. If you look at materials, they have a long history for mankind. And one of the first man-made materials for modern technologies is actually a very old system. It's called concrete. Concrete has been used for thousands of years, and it's being used to build all kinds of structures. Concrete, everyone knows. About concrete is that it's also one of the most polluting and most energy demanding materials to be made. It's based on an aluminum silicate, so you make silicates and you make aluminates, and to combine this give rise to these concrete structures. And the picture that I've shown here is that of the Pantheon in Rome that shows what it is that you can do with this kind of construction material. The crystallographic structures you see at the bottom, here they're based on silicates, silicon aluminates, and they're also the basic form for materials called zeolites that are being used for catalysis, but also for clays that are being used for all kinds of different purposes. The second man-made material that is being used in technologies in the inorganic world is steels. Here you see examples of steels, where you see the steels have enabled the possibility to make structures like this, based on lightweight steels. Aircraft have been developed based on composites, where you combine metals with polymers in order to get enormous enhancement of structures. You see here the safety shell of the modern car. This is the smart, where you see a safety shell made from modern metals. So metals is an enormous development that is still taking place all around the world. The third class of materials that is more close to the area of my own research are materials used for energy materials. This is at the moment on the forefront of research. We see all kinds of new developments, including in the areas of solar cells, where new semiconductors are being developed to derive energy from semiconductors, but also in the areas of batteries for energy storage, where you see novel materials being developed with much higher potential, much higher capacities, where you see continuous increase of the power density of these materials. In my view, a very important class of materials are related to fuel cells. Fuel cells hold the promise of harvesting and storing energy, producing energy to a very large amount. Also here, novel materials are being needed, especially the membranes that are needed in order to make these fuel cells work at high temperatures. And there is a large number of other kind of materials that is practically being researched for developing various energies. Then, if you look at where most of the energy is going, more and more of energy is being used to power the information technology that we currently have. This is a cross-section of a modern integrated circuit, where you see a modern architecture of such a circuit, where you see the hard disk drive, where the information is being stored, and you see that more and more of the energy of mankind is being used to power the information technology that enables our society. There are all kinds of principles based on this, but the basic principle goes back to the invention of the transistor, and the transistor is based on semiconductors, where the charge of the electron is being channeled by a gate that can stop the flow of electrons through a material. The flow of electron through these semiconductors is enormously energy consumptive, and this is one of the major sources where our energy goes to in information technology. In addition to electrons, we use magnetism, and another example of magnetism is also known from the old days in magnetic materials, where magnetic materials have found functionality throughout the centuries. Originally discovered in Greece, where you see the old lodestone giving rise to magnetic properties, and it has been used in navigation for many centuries, and nowadays it's being used more and more in information technology. Modern applications of magnetism are, for instance, the electric car, where you do not realize that each electric car needs, of course, electromotors, and electromotors derive their strength based on modern magnetic materials, and these are often neodymium iron boron based materials, and these magnetic materials, they consume more and more of the natural resources. Every car has about approximately 1 kilogram of this modern magnetic material. If you make a windmill, the turbines have a few tons of magnetic materials built into them. More recent is the use of magnetic material in data storage. The first data storage originated already a century ago by Palstra for his telegraphone, where he could write in a wire that was running along for 2.5 meters per second. Modern magnetic materials are being used in hard disk drives, but the trying to complete the resistance has enabled the massive densification of energy storage, giving rise to enormous data densities in the excess of 1 terabyte per square inch. This is enabled by an invention in the mid-80s called complete resistance, the ability of material to change its resistance when exposed to a magnetic field. And this is the combined power of measuring the current through a material at the expression of a magnetic field. And the change in the resistance is what is the mechanism that enables us to store data as densely as we do. It should be mentioned that this still makes use of currents, that is the charge of the electrons, in order to deliver this information. And the charge of the electron is very dissipative and consumes a lot of electricity. Less energy consuming is a different mechanism where you use piezoelectrics in order to store data or to generate information and storage. Piezoelectrics are based on Bohr materials, where the materials do not have inversion of centers of symmetry, and the extension of the material gives rise to voltage, and this voltage can be read by a voltmeter or it can be stored in data technology, also being used in all kinds of transducers, for instance for sensors, or for this fuel injector, for instance. This is a very general principle based on the non-inversion symmetry of these Bohr materials, and this is now being used in a large number of sensors for telecommunications, data storage, automotive, and consumer electronics. Nevertheless, all of these technologies consume a lot of energy. And this is also one of the challenges that we face. If we are going to a more dispersed distribution of networks of information technology, where data is being stored almost everywhere in the network, where sensors are ubiquitous in our environment, where every item will get its own information storage to give information about its value and about its data. It means that the amount of data that is being stored and is being communicated will explode over the next couple of years. This is, of course, not much of an issue because information storage can easily do its job. The difficulty is that it's consuming more and more of the energy consumption of our world. And it's becoming so large to the extent that it will consume a sizable fraction of the energy consumption of mankind. If you say that to me as a scientist, it means that you have to find new paradigms in order to store and retrieve information. And there are various possibilities that you can explore, and one of the recent developments has been to use different computer architectures. For instance, this is the Human Brain Project, where you do not use the typical architecture of modern PCs, but where you use a distributed architecture of a structure in order to have a neural network connecting many more neurons at the same time instead of the usual one input in, one input out. This is development that has been championed by IBM, and you see that IBM has already made transistors that have a neural network where many millions of synapses can process information at an enormous reduction of power, where usually the Google Brain uses the order of 100 kilovolts. This consumption of power can be reduced by many orders of magnitude. So this is one of the examples of which technology can change the way that we process and retrieve information. The way that I will discuss to you briefly now is a completely different way. And this is also based on spin, but it's based on spin currents in the absence of electron currents. Typically, magnetism is associated with the dual property of an electron, because electrons are known to have a charge and to have spins. And now it is possible to transport spins without the transport of the charge. If you can transport spins without the charge, that in principle means that you do not have dissipation in your circuit. So the challenge is then to find and define circuits that generate spin, that you can transport without dissipation from position A to position B, where you can manipulate the value of the spin, the value of your magnetism, in order to have amplification, to have detection of your spin currents. Now, these spin currents, they exist in materials of only very special nature. And one of the possibilities is not to make use of symmetry, but to make use of topology of nature. An example that I can give is a spin excitation that is no longer just the value of spin up and spin down, but where you see topology, that is the networked information of such a spin current, and the spin in the middle acts as, the object acts as an excitation, it acts as a particle. It is conserved, so that means that you can transport it without any loss of electrical charge, or any means of electrical charge. And this is an example where you see the motion. Oops. If you could maybe use the dynamics. If you click on the lower trigger, where you see this topological excitation move throughout the structure without any dissipation. So basically, you do not move a single spin, because a single spin would mean that you would also have to move its charge. But you move this as a connective excitation, and as a connective excitation, it does not dissipate any energy. The materials that you need in order to make these are very special. And the materials that you have to make in order to make these are materials that lack inversion symmetry. Inversion symmetry breaking materials are very rare, and there are only two known to us at the present moment. One is based on manganese silicide, where silicon has a tetrahedral coordination, and the tetrahedral coordination lacks inversion symmetry, and the manganese is a transition metal that gives rise to the magnetic properties. Here you see examples of these topological excitations by electron microscopy, where you see such a dense network of these so-called skromions inside the material of manganese silicide. But let me go back why it is so difficult to make materials without inversion symmetry. And the reason is quite simple. The reason is that most materials that we consider for this are based on dense packing. If you look at most metals, most oxides, all of these materials are based on dense packed structures. Dense packing means that you put your atoms as closely as possible into each other, because nature likes bonding and does not like vacuum between these atoms. If you do the bonding with dense packing, there are two types of packs. One is a cubic dense packed, called the face-centered cubic structure, or the hexagonal close packing, which is an AB stacking of such dense packed layers. This is the basic principle of any inorganic material. But you also readily see that inside these materials, all these materials always have inversion symmetry, almost by definition. The coordination of these packings of octahedral, tetrahedral, some of these octahedral environments always are based on inversion symmetry. So if you go one step further, and if you use a second element, the second element typically goes onto the interstitial sides of the hexagonal or cubic stacking. So let me give you the example of the cubic stack. If you take the cubic crossback structure, you then can put the second ion in interstitial sites, and this gives rise to a rich variety of crystal structures. If you put it on the octahedral interstitial sites, you get a simple sodium chloride structure. If you put it on the tetrahedral sites, you get the calcium chloride structures, or the zinc blende structures. Nevertheless, all of these structures are based on dense packing. Dense packing implies absence of inversion symmetry. So if you would like to have materials that lack inversion symmetry, you have to do something different. And something different is to use either elements that lack inversion symmetry themselves. And a good example are materials or atoms that have a lone pair electron, like bismuth or glass, and the lone pair displaces atoms with respect to the inversion center and gives rise to polar materials. The much easier way to do this is to use materials that do not have dense packed structures. And the easiest example of that one is quartz. Quartz, silicon oxide, is based on the tetrahedral coordination of silicon, and the tetrahedral coordination of silicon obviously does not have inversion symmetry. So here you see the crystal structure of quartz, where you see that it lacks inversion symmetry. So basically, the challenge that we have to find is to make materials that lack inversion symmetry. There are only few, or that is only two. I mentioned previously manganese silicide, and the material that we rediscovered a few years ago is based on selenides, where the selenium takes the position of silicon for this tetrahedral coordination. This tetrahedral coordination gives rise to the lack of inversion symmetry, and this means that we now have two classes of inversion symmetry less materials. One is manganese silicide, which is still a metal, and this is an insulator that can be used for dissipationist transport of information. Now, the second important mechanism to realize is that how can you transport information in these magnetic systems? Usually you send a current through your material, and the current takes with it the spin of the material. But if you want to do it a bit more clever, you have to use a different device geometry. And this device geometry is a superladder structure based on a magnetic material and a non-magnetic material. Let me explain you the working. Basically, you have a magnetic material with a superposition of a non-magnetic material on top. You can send a charge current through this non-magnetic material, and through spin-orbit coupling, ubiquitous coupling of the spin to its orbit, the spin is being deflected either in the positive sense or the negative sense. So that means that in general, if you have a charge current running through your material, perpendicular to this charge current will be a spin current. The spin current can be absorbed or reflected in your material depending on the orientation of the magnetization in this material. If the spin current if the charge current is perpendicular to the magnetization, the spin current will be absorbed and can flow. If the spin current is parallel, or the charge current is parallel to the magnetization, then the spin current will be reflected, and this reflected spin current induces an extra charge current. This charge current is what we actually measure, but it's based on the underlying spin current of your material. The materials that we make, this copper oxide selenide, needs to be grown. We grow them either using vapor transport methods, where we use a vapor transport agent to produce crystals that grow in the after vapor transporting material from warm zone to cold zone, or you can grow these materials hydrothermally in an autoclave. Both methods give rise to large crystals, and these crystals are of the order of millimeter size and are then being polished and produced for your magnetic experiments. This copper oxide selenide lacks inversion symmetry. This is the crystal structure, but if the crystal structure lacks inversion symmetry, so does also the magnetic structure. So if you have lack of inversion symmetry, also your spin structure lacks inversion symmetry, and in this case you get a chiral spin structure based in your material. The chirality is the clue by which the magnetic information is being transported and being processed. This is the magnetic phase diagram of this copper oxide selenide. We see that at low magnetic fields you have a helical spin state, where the spins form helices perpendicular to the propagation vectors. At slightly higher magnetic fields you have a conical spin state, where the spins form a cone with respect to the applied magnetic fields. And you have to apply large magnetic fields in order to get the spins aligned with the magnetic field. In a very small pocket of magnetic fields at temperatures is where you obtain these chromonic states that we will explore further. And then what you measure is the field dependence of the spin states going from this helical state to the cone state to the fully aligned ferromagnetic state. You can measure then the magnetic resistance, as I indicated. On top of this copper oxide selenide, you deposit a layer of platinum. You send a charge current through the platinum, and this charge current sends the spin current through your magnetic material, and the spin current is being detected. You can easily measure this by rotating your sample in the magnetic field, where you observe then an angular dependence of your magnetic resistance, and this angular magnetic dependence depends on the symmetry of the magnetic state with respect to the magnetism of the underlying atoms. So these are the measurements where you see the modulation of the magnetic resistance as a measure of these of the spin currents injected in your magnetic material. We have covered the entire phase diagram of this material. We see inside the helical, conical, and ferromagnetic states, you have a dependence of your spin Hall magnetic resistance that can be modeled by modeling the magnetism of this state. So this is one example to use spin currents, pure spin currents without charge currents in part of information technology. The second way in which you can do this is not using magnetic resistance, but using the so-called Seebeck effect, or the thermocouple effect. In this method, you use a heat current in order to steer your magnetic current. Basically, what you do is that you can use your charge current in order to heat your non-magnetic material. This charge current induces a heat current perpendicular to your magnetic interface, and also this heat current can give rise to the polarization of your magnons, giving rise to an angular dependence of the spin Seebeck effect, giving evidence for this spin current effect. So with that, I've tried to give you an impression of the type of research that we engage in, and I think the challenge in general is to find new methods in which we no longer use only charge currents to drive information technology, but where we also use spin currents to induce information and to transport information, manipulate information, because these spin currents, they do not have the difficulty of the electron current, which is intrinsically dissipated. And with that, I would like to thank you for your attention, and I would like to thank my group in Groningen that had until yesterday and see some of the members that were responsible for the research. And with that, I would like to thank you for your attention.
Thank you very much, Professor Palstra. And we have about 10 minutes perhaps for question and answer. Let me open this question and answer session. One person, can I have two more, if any? Okay, otherwise, okay, I'll give a chance.
Okay, thank you for the nice talk, Professor Palstra. My question is a bit specific actually, but when you grow magnetic material on top of the pattern, we have like difference in lattice, and then when you grow it, like sometimes you have some sort of like lattice strain, and then that will sometimes affect the magnetic structure. And did you see it in this kind of like CSO material, like when you grow like CSO on top of the pattern, did you see change in the magnetic structure?
Thank you. This is of course a very important issue in the sense that if you strain your material, the material lacks inversion symmetry, and because it lacks inversion symmetry, it is also by nature itself, it's piezoelectric. Unfortunately for this material, it's not easy to strain it by much. The material is very sensitive to its environment, and there are many related crystallographic structures that you will obtain if you slightly deviate from the equilibrium growth methods. So for instance, to strain the material by using different substrates is something that we have not pursued, but I expect that it will be quite difficult to grow these in an epitaxial way and to do it in this way. It's an important method, but it has not yet been researched.
Any more questions? I think there are a lot of people in the audience whose fields are material science, and they are more concerned about the synthesis of the materials. Somehow there is a gap between their concern to produce the materials and the physics that here we are seeing. That with physics we see that we can do a lot of things to improve technology, and here we see how spins, as Professor Palstra has explained to us, can boost electronic technology, not just using charge transport but spin transport. So I have a question about how far actually, since so far the best knowledge I've understood so far is that people have tried to build a spin transistor in order to be able to amplify spin current, and that's my understanding about the main issue in spin sonics. But you've just explained to us there are actually more other issues that we can actually do to exploit spin for electronics. So is there any progress that you can show that is already pretty close to application? Just curious.
There are many. Thank you for the question. It touches on many topics, of course. The question of application is basically, if you have a good concept, the concept can eventually be applied in a material. If you look into the technology of this, there has been enormous progress with any of these measures. If you look at spin injection itself has been going through revolutionary changes over the last couple of years. Spin injection, though, is always based on a magnetic metal injecting its charge into material, and with the charge goes the spin. And the detailed understanding of what's happening at that interface, where spin and charge from two different materials are being injected, forms an enormously complicated and rich area of study. The same thing can be said for spin detection. Spin detection comes in many different varieties that you can use in many different technologies. And also there you can use superconductors, you can use magnetic insulators, you can use many different device technologies to do that. If you look at the talk that I presented today, it is based also on manipulation of such a spin. And the manipulation of spin, amplification of spin, that easily can be done using the spin current concepts. The spin current concept is the concept that you use a magnon as your elementary excitation and no longer your spin. And if you use that, then you can easily see that you can amplify it also. However, the technology then is based mostly on high frequency processors, so in that sense you have to do this using ferromagnetic resonance type of experiments, and you will see that this is also being researched very actively at this point. Regarding the applicability of these concepts, look at your hard disk drive, you're using it every day. More and more of these concepts are being used. I gave the examples of the ferroelectric memories, but also the ferroelectric memory, because it's an insulator, also does not dissipate as much energy as as the conventional magnetic memories. Sony has implemented this in technology, and also that is on the market. Where I think most of the technology is moving to now is with low energy communication electronics. You heard maybe that the Dutch company NXP has been bought last week by the American company Qualcomm, and Qualcomm would like to do this for expanding on the low energy communication devices. And these make use of many of the underlying concepts that have been discussed. So yes, they are all in technology of today.
Very, very interesting. Actually, I have just one more short question. Since the type of physics or concepts, how to exploit spins for electronic technology, in the concept that you just showed, there is nothing about magnetic semiconductors. Whereas what I heard, like 10 years back, the dream of spintronics was mostly about building magnetic semiconductors, especially dilute magnetic semiconductors. Do you think that the progress along that line is somehow already dimmed because of other concepts that seem to be more promising?
You're very correct. The area of magnetic semiconductors or dilute magnetic semiconductors is very promising. And the reason that it's very promising is because silicon, of course, itself does not have inversion symmetry. So silicon would be the prime example to use it as a dilute magnetic semiconductor. But also gallium arsenide does not have inversion symmetry. So these materials, or the dilute magnetic semiconductors, they would be prime examples to study these kind of effects. Difficulty is, of course, that once you dope them and make them magnetic by doping, with manganese or with volatile dopants, they also become conducting. And at that point, you lose the intrinsically insulating properties that you have with the material that I presented today. But in principle, you are completely correct. It should also be possible with these dilute magnetic semiconductors.
Okay, thank you very much. Very interesting discussion. Since our time is up, let's thank again Professor Palstra for his great presentation.
Thank you very much, Professor Dr. Thomas Palstra, for giving such an